Welcome back. I hope you had a good morning. And the next speaker is Gurdas, and he's going to talk to you about AST. And this is not something that you hear a lot at JavaScript conferences, and I hope that it's going to be super interesting. So this is Gurdas.
So, the title of my talk is Unlocking the Structure of Your React Applications with the AST. And that looks pretty grandiose now that I kind of see it in front of me here, but I'm hoping you actually walk away with some actually actionable information. So my name is Gurdas Nijor. I'm a front-end engineer at OpenGov, where we build the world's premier business intelligence platform for governments. So basically around late 2013, while in the midst of a kind of backbone-related meltdown, I remember watching Pete Hunt's really influential talk, Rethinking Best Practices. And a quote that really stood out to me was this one from Dijkstra. I'm sure you guys have all heard it a few times by now, but I think it's great, and it kind of does a good job of kind of setting the stage for my talk. So we should do our utmost to shorten the conceptual gap between the static program and the dynamic process, to make the correspondence between the program spread out in text space and the process spread out in time as trivial as possible. So I think this quote does a great job of revealing one of the overarching goals of React. And it tends to get overshadowed by some of the really kind of cool details like virtual DOM. And I think it really bears mentioning here, since it really does a great job of framing this talk. So it's the static nature of React through the invariants that it provides that not only make applications easier to reason about, but provides us, it opens the doors for some interesting techniques and tools that I kind of want to talk about today. So just to get a definition out of the way, I've been throwing around the term static a lot. It's in the context of static analysis. So this is basically being able to analyze an application just based on the code. So it doesn't involve having to actually execute it, and you don't need anything to happen at runtime, basically. So let's take a look at what has often made static analysis difficult in the past, and things React has done to kind of stay closer to the nature of Dijkstra's quote. So first of all, I'm going to kind of pick a backbone a bit. It's an easy target, but so basically, what has made static analysis difficult in the past is the fact that this applies to pretty much any kind of view-like structure that maintains its own kind of DOM internally. So the issue is that you, at any point of an application, you can mutate this DOM. So that could be within the view itself. It could be in client code. You have no consistent way, just by looking at a file, what visual representation you're going to see. So technically speaking, its rendered output is not a pure function of its input data. And it can't really be known until runtime. So another thing that makes static analysis difficult is our previous notions of separation of concerns. So we would typically have a template file external to the view that would be imported in with some varying different mechanisms. It could be sitting on the document itself. It could be required in, and it could be authored in some arbitrary templating language. And so just based on looking at this file, it's completely opaque, and you can't really determine what the end visual structure is. So let's now look at what React does to make static analysis a lot easier. So the first thing you notice right off the bat is that everything you need to know about a component is defined within this React create class call. So there's no, it's not spread out. I mean, so from a logical and physical perspective, everything you need to know from the lifecycle methods to the rendered output is right there pretty much. But the more powerful aspect that makes static analysis easier is the fact that React components visual representation can effectively be thought of as a function of its internal state and its props. So there's no hidden runtime state. So what you see is what you get. So we're going to explore the implications of this a bit more when we get to the actual building of our static tooling. Which brings us to the next point. Where is this analysis and transformation going to take place? So we're already performing static transformations in code today. Most of us are using some form of a build system. Could be Grunt, Gulp, Webpack. It doesn't matter. They all have steps to basically take some semblance of source input, run it through a variety of transformations and other kinds of different ways to transform your code. And and as a result, you end up with static assets that you can end up serving to clients. So one thing that all of these kinds of build tasks have in common is that they're really low-level transformations of code. So they operate at the level of syntax, they operate at the level of minification, and various kind of low-level concerns. So since we've already shown that React components, and by extension applications built with them, have invariants that make it possible to reason about and analyze them at build time, why don't we use those properties to expand the scope of what we do at build time? So what am I kind of thinking here? So I'm thinking of higher level transformations with knowledge of React's component API that can basically plug into a build system as they do any other task. So you can think of new use cases like instrumentation, so that you would inject code into your application for the sake of collecting information and other kinds of concerns like that. You can think of component catalogs, where you can actually have your entire source tree can basically be taken as an input, and you can basically comb through that entire source tree, pull out the actual components and host it in some kind of single-page application that acts as almost kind of like a living component catalog. Or you could have documentation. You could just have a static representation of all of your components within your application. So let's kind of focus on one use case that can have some practical value today, the instrumentation of an application. So instrumentation has typically been the domain of code coverage and performance tools. But let's see how it can be used as a development tool in exposing information in a running application. So this really awesome blog post from the folks at Circle CI, it gives you a really good feel for some of the challenges involved. This blog post, it relates to recovering the concept of component local state and OM components. But it brings up some really great, more general points about the challenges of instrumentation in general. So let's take a look at a way of kind of working around this for the purposes of building a powerful development tooling. And to make our discussion a little more concrete, we're going to pick an app that we want to instrument, and that we could generalize that to any transform that we run against any application. Anyone want to guess which application that'll be? Yes, there you go. How did you? Yeah, it's amazing. So yes, yeah, to do MVC, woohoo. Please stay in your chairs. Don't get too excited. So how are we going to approach this? So we want to see how props change between update cycles for every component in this application. So here's our strategy. Anytime a parent passes new props down to a child, the child will publish the current and change props to an event emitter. And basically, a component on the right side will be responsible for subscribing to that event emitter and taking the current and change props and then showing a visual diff of what those look like. So I want to show a demonstration of this just to make this a little more concrete. So I'm going to go ahead and get that switched over. Sweet. OK, so what you'll see here on the right side is that panel component that we were just talking about. This was run against Flux to do MVC. There were no source modifications made. And what you can see is as you kind of interact with it, you'll see on the right-hand side that you'll see almost something that looks like a diff of the props for a particular component. And this just happens on a kind of running basis. So as you interact with it, you can kind of see that as like an activity stream of your component's props as they receive new data. So that's pretty cool. So let's get into how we're going to implement that. Can I get a switch? Awesome. So here's a logical view of the component hierarchy for this application. So we're going to walk through some of the modifications needed to build this kind of instrumentation. So we're going to zoom in on the main section component and its own to-do item component. So from a really high-level view, you can just see that the main section is passing props down to its to-do item. So we're going to need a way to basically have the to-do item in some way figure out that props have changed since the last update cycle and dispatch that to the event emitter. So to do that, we come up with a concept of a component wrapper. And what this component wrapper does is it receives a cloned copy of the props passed from the parent for the reason that it could be passed a reference to an object that may not change, or it's not going to change between update passes. So we need the parent to actually clone it before passing it to that wrapper. And that wrapper will be responsible for publishing that change to the event emitter. So that makes the component wrapper's implementation pretty simple. I mean, its component will receive props, basically just has to do a deep equality of the current props and the props that it's been passed, basically, at that point. So let's get into the code. There's the before, there's the after. One thing to note is that the to-do item itself, it's still present in the actual render. The difference is that it's now wrapped by the component wrapper. Another thing to note is that props are still passed in, but the difference being that we have to clone the props before passing it to the component wrapper for the reasons that we kind of went over before. So we perform this modification for every component in the entire hierarchy, and we've fully instrumented this application. So that's all good and well, but how do we safely generalize this transform? Because we want this transform to be reusable as something you can just plug into your build pipeline for any application. It shouldn't matter. It's not going to be just localized to do MVC. I'm pretty sure we have more applications we work on than that. So this generalization, we couldn't even talk about it if we didn't get the static guarantees we get when using React, which safely let us treat a component as a function of state and props. So obviously wrapping it is not going to cause any kind of negative kinds of side effects. So that lets us focus on the actual mechanics of transforming code. So how do we do that? Well, lucky for us, there's some pretty well-established tools for this entire class of problems. So here's a really, really high-level view of a compiler, a bunch of detail omitted. But from a basic perspective, a compiler's purpose is for taking a higher-level source language and basically producing a lower-level source language. For instance, taking C++ and converting that to machine code. And something closer to our domain is our transpilers, basically. Taking a source syntax like ES6, converting to ES5 or what have you. But we're going to go a step even less than that. We're going to start with the same source, and we're going to end up with the same output. Lucky for us, there's a number of ways to kind of achieve this goal. So the first step, or the front end of the compiler, consists of actually taking input source and parsing it into an AST. So the library I'm using for this is Esprima. It's a really popular a JavaScript parsing library. There are a lot of other alternatives out there, but we're going to go with Esprima here. So jumping straight to a definition, what is an AST? So from a really high-level perspective, it's basically just a tree representation of the syntactic structure of your code. So for instance, you can have a function declaration. You would have an arguments list would be a child of that, and the body would also be a child of that. And that structure basically captures your entire syntax across your code. So just to give you a feel for what Esprima's API looks like and the resulting output, Esprima.parse will just take a string representing your code, and it'll produce that syntax tree. The program will be the top level node, and then everything else kind of descends down from there. So the terminal step involves the generation of code. So this is we're basically flipping the process of parsing, taking the AST, passing it to a code generator, which we're using scodegen for this purpose, and it produces code. So API for this, very basic, very simple. You pass in the AST, it gives you code back. So that's all good and well, but the interesting part is what happens between the parsing and the emission of code. This is where we're free to basically manipulate the AST and do whatever we want to. That's syntactically valid, of course. So I'm going to go over a number of tools we can use to kind of work with the AST. One of the really big benefits of having a tree structure is that so much of computer science is dedicated to the study of trees. So In terms of traversal and query, ES Traverse is a really popular way to do this. It's a pretty basic API over a depth first search. So it exposes enter and exit methods that basically, as you're descending down your tree, enter will be called on the way down, and exit will be called on the way up. So it's a pretty simple way of traversing your tree. Another way, if you like a kind of like CSS selector syntax, is ES query. So this is pretty cool. You can pass it a string with something that looks like you'd pass to like selector all or a jQuery selector, and it'll actually return you all the matched AST nodes. So for construction and modification, to build new AST nodes, you can use a fragment parsing technique. So this is something where we just use Esprima's own API. Pass it a string representing code, it produces an AST that you can use. Another is Benjamin's AST types, which he uses in Recast. This is pretty cool. So this is a way you can incrementally build up AST using kind of like a builder API. So now we get to templates. And at this point, some light bulbs are probably going off in your heads. This looks a little bit like something we used to do, which was work with a DOM. And in a lot of ways, there are some similarities in between the two. With a templating approach using ES template, you can basically pass a string representing the output of the code you want with some delimiters. That it looks almost like like an underscore template or something like that. And you can pass it basically nodes that you want to be in the resulting AST. So, and finally, we could just use object literals. I mean, these ASTs, they're just JavaScript objects, so there's nothing exotic about them. We can build up a literal and add that to any point in the AST. So with these tools in hand, let's look at how we'd go about accomplishing our goal of actually transforming our code. So this is an example of a module that would take sources and input, wrap every single call to create element with a component wrapper that we're using for instrumentation. So the first step is that we parse that incoming source into an AST. The next step after that is we have to determine whether that AST, as we're basically traversing the AST, figure out all the places where we see React.createElement calls. So to do this, we basically determine this with a pretty simple conditional check on the node that we've traversed to help you better visualize what a React.createElement call would look like in terms of AST. There's a lot of good tools for doing this kind of visualization. But what you see on the left-hand side is the actual source, the input code, and the right-hand side is the parsed AST. So you can see the structure there. So we're looking for React.createElement calls, but more specifically, we're looking for React.createElement calls that have an identifier as their first argument, for the reason that indicates a React class. So it indicates a component that we want to wrap, basically. So if that's the case, if we found that React.createElement, we can basically use the fragment parsing technique that I talked about earlier to basically parse a little kind of wrapper representation of the AST that we're going to basically add additional information to. So the next step is we basically take the component name, we take the props from the current node that we've traversed to, and add that information to the node, to the wrapper AST effectively. And the final step is that we just basically return that node, and that will be basically injected into the greater AST. And this process happens for the entire source file, and it effectively traverses through and instruments pretty much all your components. So let's have a little fun. I'm going to jump back to this demo, and there's something I left out. But probably didn't notice this the first time. But there's a little 3D button here. And with this 3D button, you can visualize your component hierarchy in 3D. So this is, yeah, 3D every time. It always gets them. This is really cool. I mean, it's kind of like the Firefox 3D developer tools if you guys have played around with that. But it works for React components. And why am I showing this now? The reason I'm showing this is that I want to make the point that we're free to build any kinds of development tools we want using these kinds of techniques. The sky's really the limit. I'm sure this does have some practical applications too, but yeah. Okay, so just jumping back. So how do we productize all this? How do we package it all up? It's all good and well to have these things that'll transform code for us, but how do we kind of make use of this? And Brent gave a really good intro to Webpack. I'm not going to do any kind of deep dive. I just want to give a really kind of basic intro to Webpack's concept of loaders. So loaders are basically just functions. They take source as an input, and they pass source as an output. And anything you do in between is up to you. So all the transformations that we went over before, we can actually have running inside the context of a Webpack loader. But the more interesting part that loaders kind of provide for us is that we have the ability to basically inject runtime dependencies at the time of our build. So that's the way we were actually able to add that the panel in. We're able to add in some of the components to manage the 3D rotation. That's how we were able to add the component wrapper. With this, you can basically have runtime components that support your transformations as well. So it makes for a pretty powerful kind of pattern for building out these kind of higher level transformations. So in terms of conclusions, we saw how React, its invariance really let us kind of extend the boundaries of what we can do at build time as well. It's got obviously really, really awesome, runtime properties, but I'm also really excited about what it provides for us at the time of build. We looked at, how we can use AST transforms to do, instrumentation of a React application. But like I showed before, that's just one use case. I mean, there's so many different, there's so many other ones that we can kind of look into. And we also looked at an approach for, packaging these transforms so that someone can basically npm install and they can immediately start using in their own applications today. So with that being said, I'm free to take questions.
I noticed you clone deep the data.
Yes.
Are you sending this data only for the event emitter, or are you passing the cloned object down the React tree? And how does it play with immutability and with performance in the instrumented code base?
Yeah, no, it's a great question. So in terms of what it provides you, so it's a pretty basic approach. I'm just doing a JSON stringify and JSON parsing that. So we basically just want the ability to have whatever data that's JSON serializable is what we're trying to show. But is your question about in terms of performance? I'm sorry.
Yeah.
Implications for that?
Yeah. Implications
so this is stuff that you don't want to run in production. I mean, this is mainly this will be a tool that you'll typically have as a development tool. But yeah, it'll definitely have performance implications, and I'm sure that's stuff that with more time we can figure out some ways to optimize it.
And does it cause any side effects about immutability? Since you're passing, like, let's say I have an array of data, and then I want to generate an array of elements. I don't want to re-render the parts that don't change, right? Yeah,
so one of the big downsides of the fact is that, like I said, the data has to be JSON serializable as you pass it down. There could be some other approaches where you can make it that serialization, you can make it pluggable. So that at build time, you can, like if you're using immutable JS or something like that, you could have a different semantic for actually being able to provide that.
Okay, thank you.
Yeah. Any others? Yes.
Yeah, so rewriting the AST essentially lets you instrument stuff, but it would also let you basically create syntactic sugar for things that are hard to write or complicated to write. And so you could potentially run something like that in production, or at least in a transform step.
Correct.
For instance, the JSX step? Have you thought about maybe actually using this as sort of like a bootstrap to actually bootstrap React?
In terms of JSX, can you? I'm sorry, I didn't quite get that.
So JSX right now is a transform,
yes.
right?
Yeah.
But at the end of the day, it could also just be something that is simply generating an AST.
Correct.
Right.
Yeah, that's another way to look at it. Yeah, right now it is a transform. It'll transpile to JavaScript, and there could be another kind of tooling chain around that. But yeah, the way that I'm kind of looking at it from this perspective is that I want something that will basically be able to transform at the API level. Basically, I mean, yeah, you could look into maybe taking the AST with what's provided with JSX as well. But I wanted basically just to work with the ES5 AST.
Okay, thanks.
Yep.
In terms of having everything on the page, or in the same file, that gives you everything you need to know about a class, one of the things that breaks that is mix-ins. So I was curious as to whether you ran into any trouble with sort of areas like that, and if so, how you got around that, or how you dealt with it.
Interesting point. So the thing is that with mix-ins, you can't actually override a render method. So that's one of the really important things to kind of take away from this, is that the class will just define whatever whatever's you're capable of rendering effectively. So a mix-in can't change that behavior.
Okay. Thanks.
Yeah.
Hey, we really love Webpack, but it operates on a string and puts out a string.
Yes.
Is there any way that you could kind of use like the Sweet.js, use that to do the same thing, where you would be operating on a token stream or an AST and spitting out an AST?
Yeah, I mean, it's an interesting approach. So what Webpack kind of provided that I really liked was the fact that with loaders, that you're able to get the runtime dependencies also injected. So with Sweet, it makes a lot of sense if you're just doing straightforward syntax transformations. So with this, there's a little more kind of infrastructure needed to kind of pull off that transformation.
You can do runtime stuff soon.
Oh, you can soon?
Because macros will have runtime dependencies quite frequently.
Are you working on that right now?
I used to get into it.
You got some commits?
Don't hold me to it.
Okay.
Hi. Why not just use a mix-in for the instrumentation? It would save the cloning.
Mix in for the instrumentation.
Yeah.
So yeah, okay. So
just add in the mixing in the transform.
So
that's
there's
it.
there's actually the reason why the wrapper was used in the first place is there's actually some rendering happening that actually there was actually a little kind of flash that you can see around the borders.
Yeah, the 3D
components.
view and things like that.
Yeah. Well, that, and then also the fact that mainly for the fact that we need the ability to kind of extend what's happening with render. So that kind of that's kind of justification.
Yeah,
for that.
But just for the event emitters.
Yeah, I mean that's another approach. Yeah, you can wrap that into a mix-in, and then you can have that injected at build time, and then that's another approach too if you want to break it up. Yeah, excellent point. Any other questions? Okay, great. Thank you so much.